record and then make it available to you after. Okay?
Fantastic. Thank you so much.
Sure. Yeah, no problem. So I'm going to skip all the marketing fluff that you saw me scrolling through a minute or two ago and dive directly into what scale actually is. Okay? Starting, decade and a half ago, we took a very close look at how infrastructure was being done up to that point from a virtualization and containerization perspective. And we discovered something kind of sad, really, that virtualization was never something that was purpose built in the x86 space. In fact, it started life as a almost a science experiment in the EDU space out at Stanford to see if you could bring the concepts of AS400 and mainframe, high availability, fault tolerance, so on and so forth, into the x86 architecture. Now, that was obviously absolutely done. And in doing so, did some really cool stuff. Sorry for the history lesson, but I think it's kind of important to set the table before you eat,
No,
right?
I love it. Sorry to interject, but I love the analogy with the mainframe because that is where I started my tech career. And I was telling my virtualization team the other day that, VMware wasn't groundbreaking stuff. We had virtual partitions on mainframes way back.
Oh,
So
yeah.
it wasn't new.
In my time at IBM, far longer ago than I want to admit to, I recall a rainstorm and hailstorm at IBM Boulder, dumping so much rain onto the roof and so much hail that it caused the drains to back up,
Mm.
caused the roof of the data center where the AS400s were kept there at IBM Boulder to cave in a bit, shorted some stuff out, lost power. When the backup generators kicked in, about half the AS400s would not boot. And the reason why is they had been running for so long that when the drives spun down, they seized. That should tell you how highly fault tolerant the entire mainframe architecture was. They'd
Absolutely.
lost drives and component pieces and nothing had ever gone down historically. So jump forward about 15 years from that point. So yes, VMware did in fact, Stanford, I should say, did in fact move the world forward in the x86 space by bringing the concepts of virtual machines to that space. And in doing so, radically simplified what infrastructure should look like.
It's a
Some of the lead
technical
members of that team
extract
actually
relevant
left and
information
formed VMware.
and develop the project schedule. Now, why do we care about the schedule? Well, the schedule helps us identify when each specific task should begin.
Sorry, Sam, I muted you there. You were kind of coming through. You can unmute yourself whenever you like. Um,
Apologies.
so,
It was a YouTube video that started on my side. Apologies.
oh, no worries. So, long story made very, very short, that took a whole lot of the extra expense out of running infrastructure. Suddenly, instead of having to have dedicated servers for file and print and domain controllers and application servers and, instead of needing, 6 or 10 or 20 boxes, you only needed one. The downside was when a power supply failed, when a motherboard went up in smoke, etc., you didn't lose just one function, you lost everything. So to solve that, highly available storage was borrowed from the database space, believe it or not. Originally multi-homed physical SCSI, then later Fiber Channel, followed by iSCSI because Fiber Channel is exceptionally expensive. and made up for it by being incredibly complex, um, to bring high availability into the virtualization space. Now, the cool part about this is it gave us the killer app that made VMware a must-have, something that had never happened in the virtualization or in the x86 space before. The ability to lose a component and have everything stay running, live migration, fault tolerance, so on and so forth, made it the killer must-have. The downside, all of the cost and complexity that you got rid of by virtualizing in the first place, well, that was brought back and amplified. Suddenly you needed to have, quite frankly, somebody on staff that was a VCP and a CCNE and a SNIA certified storage engineer so that all of the pieces could be bolted together. The upside was, well, the killer app made it worthwhile. The downside was all of the expense and complexity came roaring right back. So what does all this have to do with scale? Well, what we realized back in 2007, 2008 was all of that complexity of borrowed pieces of technology from different technology domains was the root of the problem. The virtual infrastructure, historically speaking, had never been cohesively built from the ground up to do a specific job. It was an amalgamation, a layer of the layers of an onion, if you will. So what we set out to do, and what we do to this very day, is we purpose-built an infrastructure from the ground up for all of the pieces to play together natively. Get rid of the complexity. We started leveraging AI and ML 15 years ago, before AI and ML were even buzzwords in any meaningful sense other than in Hollywood, to automate as much as is absolutely possible inside the infrastructure. I'll get into how all of that works very specifically here in just a few. So what we set out to create was a virtual infrastructure that you didn't need to be a VCP and a CCNE and a SNIA certified storage engineer, but rather you could take a kid straight out of the local community college, still waving around his A+ cert like he's the first human to ever get one, and have that guy able to stand up infrastructure, set up workloads, do live migrations, set up DR, and only need maybe 15 minutes worth of training to do so. Okay? Equally, if not more importantly, do it at a price point that makes sense for the real world. You know, rather than the 1600+% price premium pre-Broadcom that you'd see over and above the cost of the gear it runs on, the hardware it runs on, we wanted to make infrastructure directly approachable by folks that needed it the most. The SMBs, the K-12s, the city hubs, the county hubs, so on and so forth. So that's what we built. Okay. And along the way, because we took such a purpose-built approach, highly automated purpose-built approach, it allowed us to do some things that neither VMware nor Hyper-V can do to this day. For example, this last line on here, grows with Moore's Law. I mean that very specifically. Literally, I have customers that started with Scale over a decade ago with old Xeon X3450 quad cores that added Sandy Bridge and Ivy Bridge and to that infrastructure, hot and on the fly as they go, and have it all play nice together and happily live migrate back and forth between. That's something that even enhanced compatibility mode in the VMware world has never been able to do. If it was close enough, it would let you by whacking all the extended x86 feature sets, but with Scale, that's always been the case. You just can grow as you need based on the technology of when you're ready to grow, rather than having to, overbuy on the front end like mad and then throw it all away 5 years later and start over. So let's dive into what the moving parts are and how they actually work. And like I said, questions, comments, concerns, fire away. This very much is your time to discover what it is you'd like to know. The moving parts of the scale computing platform from a 90,000 foot view are what you see on the screen. HyperCore is our OS, runs directly on the individual nodes themselves. And that's where I'm going to focus most of the time in this discussion on. Fleet Manager is a tertiary product that allows for the management of multiple sites, from a handful to tens of thousands of sites from a single UI. I'll get into how all that works here in a bit, but let's focus here for the moment on HyperCore. Now, I hope you guys don't mind. I'm going to do a little bit of finger painting here, just purely because I think it will help make sense to understanding what a scale cluster is and how it specifically works. Okay? Regardless of the size or type of the nodes, they all work exactly the same way. From the smallest of the small, heck, our stack fits unmodified on things as small as the Intel compute card, the Element, the NUC, all the way up through the 1U, 2U, multi-U implementations scaling up into the petabytes. But it always looks, acts, and works exactly this way. A scale cluster starts life as a series of x86 server nodes. When it ships to a customer location, already layered onto a small partition on drive 1 of every node in the cluster is a copy of our OS. As I mentioned a moment ago, it's called HyperCore. Now, HyperCore is a Linux derivative, but every single thing that doesn't need to be there is not only inactivated, but actively removed, and all of our IP is layered in, okay? The cluster orchestration stack, the management stack, the DR stack, the storage stack, the hypervisor itself, the AI and ML engines, the state machines, all done before it ever even arrives directly on bare metal. Now, this partition is mirrored onto an identical partition, and it's small in size, few gig, okay, on every other drive in the node for obvious reasons, so that if a drive goes up in smoke, it doesn't affect runtime at all. It doesn't affect the running workloads at all. Okay. Now, it's at this point that things diverge fairly radically from what you're used to seeing in a virtual infrastructure. The first thing I'm going to point out is actually something you don't see here. You don't see a third baseman management server of any kind. You don't see a vCenter server or a System Center virtual machine manager or a Rev manager or a Prism instance or any of those things. The reason why is we don't need one. One of the first things we did here at Scale is borrowed a concept from the high performance computing space called state machines. Now, state machines are a series of multi-threaded demonized processes that run in HyperCore on every node in the cluster. And what they're doing is both simple and complex at the same time. They are signatured to know exactly what the hardware is that they are running on, all the way down to the chipsets level, to the revision of firmware running on said chipsets, down to the BIOS level of the nodes themselves. Okay? They know exactly what the hardware is, and by extension, what states it can get into and what the remediations are for those states. In real time, they're tracking everything going on from a physical, logical, and runtime perspective on the nodes. From a physical perspective, they're tracking the state of the power supplies, the state of the NICs, up, down, drops, retransmits, signs of next, fexed, so on and so forth. Okay? They're tracking the state of the drives, the state of the drive controllers. From a logical perspective, they're tracking which workloads are running in CPU and RAM on the nodes, at what performance levels, at what load levels. They're tracking the exit codes from SCSI write commands, SCSI CDBs. When a given SCSI CDB takes longer to commit to disk to get to exit 0 than it should, they know when to retry that write, when to send that write to a different block on a different block device, when to reset that drive, when to reset the controller for that drive, when to drop that drive, all without a human intervention of any kind. Heck, they even know when to drop the entire node out of the cluster. Okay. Now, notice this guy right here, backplane switch. This can be a VLAN off existing switching. This can be a dedicated switch. This can be dual redundant dedicated switches. This can be gigabit. This can be 2.5 gig, 5 gig, 10 gig, 25 gig, 40 gig, 50 gig, 100 gig. It's entirely up to you based on your use case and the infrastructure you're implementing. Okay. It is layer 2 unrouted. It's used for a couple of very specific things. The first of which is those state machines talk to each other in real time so that every node knows everything going on every other node as it happens without needing to reach out laterally to a external management server of any kind. Okay. You know, I'm a big one for analogies, and the closest analogy I can give you here to what this infrastructure looks like, what the legacy approach to infrastructure looks like, is actually a story from when we were designing HyperCore in the first place. You see, let's say you're sitting in your backyard, 6-foot privacy fence all the way around, and the other side of that privacy fence, you hear your neighbor banging away in their backyard, making a heck of a racket, right? You want to know what they're up to. Well, if you follow the legacy approach, the VMware / Hyper-V / Rev / Zen / Nutanix approach, then what you would have to do is go into your house, sit down at your desk, write a letter to his mother in Cleveland, mail it, wait for her to get it, open it, read it, write a letter to him, mail it to him, wait for him to get it, open it, read it, write a letter back to her, and her to get back to you. Or you could do what we do in the real world, which is lean over your fence and talk to your neighbor. Well, that's what scale does. Making this entire redundant legacy piece of the infrastructure pie simply go away. It never needed to be there in the first place. This is part of what I meant by purpose-built rather than an amalgamation. Now, the state machines, as you may or may not have gathered, they don't stop at observation. We always, in every single case, know exactly what the hardware is down to the chipset level. We know exactly what states that hardware can get into and what the remediations are for it. So we took the time with the state machines to build in all of the OODA loops, all of the if you see this, do that. Okay? Now, what that translates to is the state machines, they know that when they see signs of drops and retransmits increasing on a NIC dropping offline, signs of alien crosstalk, next or FEX, they know when to just go ahead and fail over automatically to the partner NIC on that node. Like I talked about with drives a mere moment ago, they know when to do what to compensate and keep things going. Okay. Now, this leads directly into the next part of the infrastructure discussion, the storage stack. When you stand up a scale cluster, nodes out of the box into the rack, cable up the Cat6 or the SFPs or QSFPs or SFP pluses, depending on what your infrastructure is. Okay. Hand out IPs and hit the initialize cluster button. First thing that happens is the state machines discover what kind of nodes they're running on. They then discover the other nodes in the cluster. They form the cluster automatically. They then fire up our storage stack. It's called Scribe. And please note, this is not a file system. File systems, again, way too much overhead, way too little benefit. Rather, it is a low-level block control engine. Scribe gets fired up, goes out and discovers every single block device of every type in every node in the cluster. Fully enumerates the block and cylinder counts of all of the drives in all of the nodes, creating a single global namespace of disk from all of the drives in all of the nodes at a block level, not even a block device level, all the way down at the individual block level. Okay? We take low-level control of all of the blocks everywhere. Scribe then goes and subdivides that global namespace of disk based on the types of drives it finds, putting all of the NVMe drives into their own tier, or SSDs, flash, into its own tier, all of the spinning Rust, legacy HDDs into their own tier. Now, notice there's no initiators here. There's no targets. There's no LUNs. There's no need for any of the above. There's none of the overhead of iSCSI ARB, ARB win, SCSI reserve, SCSI release. There's no object files sitting on file systems, sitting on object files, sitting on file systems. We don't need any of that legacy cruft. Dive into that here in just a minute. But essentially, Scribe works via libaio and libscribe. Every time a virtual machine wants to write a block of data, it writes it to a minimum of 2 separate blocks on 2 separate drives on 2 separate nodes in the cluster with a simple T, fork, and flush. Okay. Both copies of a data block are used active-active. Okay. Speeds up reads a ton. Simultaneously, their placement is fully dynamic. We will automatically move those data blocks around based on hotspotting, based on heat mapping, based on frequency of access and use. There's a really cool little override in the UI that I'll show you here in a bit, but we will automatically move the slower blocks down to slower tiers of storage and faster blocks up to faster tiers of storage without you needing to do a darn thing. When you move your workloads over into a scale cluster, it figures out over the first 24 hours of runtime which blocks really need to be where. Okay. Now, before I move on, are there any other questions at a fundamental level about how this works, or is this making sense to you?
I think so, yeah. I'm trying to kind of compare it, possibly the Scribe to maybe storage spaces, but Microsoft, having the single namespace for storage, but there's a lot more overhead and complexity, and it's running through the CPU in that case.
Yeah, that is very, very true with storage spaces. And then you've got to let the layer in of NTFS sitting on top of NTFS, etc. Scribe, think of it this way. You've stood up storage spaces direct and failover cluster manager and system center virtual machine manager and so on and so forth. You know what goes into standing that infrastructure up. Standing up an equivalent scale cluster, this is your experience. Nodes out of the box into the rack. Cable up the network infrastructure. Okay. Hook up a KVM to the VGA port and USB port on the back of each node. Hit the power button. The nodes come online and ask you exactly one question. What's my IPs? LAN and backplane. Nodes take the state machines take low-level control of the NICs themselves. Hand out the IPs. Do that on each node. Takes about 1.5 minutes per node. When you get to the last node in the cluster, after you give it its IPs and the IP of the first node in the cluster, hit the initialize cluster button, disconnect your KVM and go grab yourself a cup of coffee or a Mountain Dew or, whatever's appropriate for the date and time and mood, so to speak. Come back about 15 minutes later and point a browser at any one of the node land side IPs, doesn't matter which, thanks to the state machines, all roads lead to Rome. You're up. Literally from gear in the box to I'm ready to carve a VM, call it about 18 minutes, bell to bell. I'll let you draw your own comparisons to what you've stood up with Hyper-V and Storage Spaces Direct historically, but I think you can see the difference.
Oh,
here.
Absolutely.
Yeah, there's a reason that the term hyperconverged.
Discovers everything.
Oh, go ahead.
Yeah, it auto discovers everything.
Yeah,
and that would be the case as well, changing out a disk or a node. It's automatically going to learn it.
Well, I'll show it to you. So, and I apologize in advance to everybody. I'm a lot of things as a CTO, but a graphic designer is not one of them. So I apologize for the horrific animations you're about to endure, but conceptually it should get the idea across to you. Simple 3-node cluster, node 1, node 2, node 3, state machines running on each node, talking to each other over that backplane network, right? The various virtualization layers, the scribe virtual hard drives. Now, bear in mind, virtual hard drives in a scale world, there are no VMDKs or VHDs or VHDXs or QCOW2s. There's no such concept as a data store. We don't need any of the above, okay? The data placement algorithm and backplane network. Now, notice what happens as a virtual machine starts writing blocks of data to the cluster. Okay. Those blocks are round robin chain committed to a minimum of 2 separate blocks on 2 separate drives on 2 separate nodes in the cluster across all drives in the cluster. Okay. So when, as you just described, a drive goes up in smoke, there is none of the legacy cruft around RAID overhead, RAID penalty, and RAID rules. Yep. Let's boil this down a bit. We're all admins here. When you've done the legacy approach to virtualization, brought in somebody's storage platform, set up your RAID levels, usually RAID 5, RAID 50, RAID 6, RAID 60, any of the erasure coding based approaches. What happens on a drive failure there? Let's say that you've got a 5 drive plus a hot spare RAID 5 array. Okay. Drive fails there due to heat and vibration over time, right? It gets dropped out. The controller for that RAID set's supposed to see that, drop it, sub in the hot spare, and then start rebuilding the hot spare, white space and all, from the parity stripes across the other 4 drives in that RAID set. Side effect, ramping up heat and vibration that just took out a drive, trying to rebuild one to match the failed drive, right?
And there's no putting things into maintenance mode.
No, absolutely not in that state. Now, here's where things get fun. Your performance tanks. Absolutely tanks. Because your drives, your surviving drives, are now doing what? 4, 5, 6 times the amount of I/O, trying to service ongoing I/O while also doing mad reads from all of the drives and mad writes to the failed drive, to the hot spare, right? Now, scale world. Drive fails, drops out. We detect that. Scribe sees it, state machines flag that drive as offline. Every single block that was on that drive active block has a mirrored active copy spread across the, in this case, 11 other drives in the cluster. Okay? We don't rebuild a hot spare. We don't need to. 11 drives talking to 11 drives, straight block copies. We simply reduplicate those data blocks and continue. No rebuilding of white space, no none of that. The only thing you've actually lost when you lose a drive in the scale world is the capacity that drive contributed to the cluster as a whole. Now, we replace that drive. That's on us. We send you the replacement. Pop out the failed drive, pop in its replacement. We're not going to rebuild him. We don't need to. We've long since exited the exposure window. We simply start sending new data blocks to him and rebalance in idle thread across the cluster as a whole in the background. All you've done is given the capacity back to the cluster that one drive was contributing. Order of magnitude faster exiting of exposure windows and dealing with component failures. Now, this same concept applies, like you mentioned a few moments ago, to losing an entire node in the scale cluster. Remember those state machines talking to each other in real time. Every node not only knows everything going on every other node, but knows which workloads are running in CPU and RAM where, and has full copies of every data block associated with every single workload. Entire node goes up in smoke. State machines on the other nodes detect that that node has stopped responding. Its state machine isn't talking on the back-end node-to-node subnet anymore, right? Well, they start a come back to life timer just to make sure it's not a congestion issue or something funky on the back-end node-to-node subnet. That timer expires, well, they already know everything that was on that node. Their workloads are completely unaffected, so they simply move the workloads over that had been running on the failed node and restart them on the surviving nodes, again, without a human having to do anything. The concept here is simple. In the event of a node failure, recover faster than an end user can figure out something is wrong, get to a phone, and call the sysadmin to say, hey, something's wrong. Have everything back up and running, with workloads that weren't on that node completely unaffected. Lose any drive anywhere at any time, lose any entire node anywhere at any time, and everything just keeps running. Make sense?
Yep.
I'm going to skip past this. This is mostly just about the data placement algorithm. And we can go one of a couple of different directions here. So I want your guys' input on which direction you want to go. We can either go into why we did so much reinventing of the wheel, right? What the competitors and competitive space looks like, or we can dive directly into some of my running clusters here in my lab. What works best for you? What would you like to see more of, dive into more deeply? I throw it out to the group. Which way would you guys like to go?
So from the perspective of the Tecomec guys, I think you probably would like to see a live demo of the environment of your environment. We've gone through quite a bit of information on on that.
Sure. Okay, no problem. So nodes out of the box, into the rack, cable them up, hand out IPs, hit the initialize cluster button, went and got a Jack and Coke because it's late on a Friday, came back about 15 minutes later and pointed a browser at any one of the IPs you just handed out. You're up. Okay. Log in, dive directly here into the settings tab, hand out your environmentals, the basics, give your cluster a name, a DNS for the site, NTP server, because clusters love to stay time synced, where to send alerts, who to send them to, IP for a syslog server if you want to harvest syslog data. The basics. From here, you're going to jump up to the Media tab. Now, the Media tab is the closest thing you will find in the entire Scale universe to a data store. It's literally just a home for a couple of things. One, ISOs. Drag and drop your ISOs directly into the browser window. Okay. It also is a home for dragging and dropping your VMDKs from your legacy environment, your VHDs, VHDXs, QCOW2s, and so forth. You can drag them in, drag and drop them in, and we will lay them out in Scribe, but keep the identifier names of the legacy file names so that you can simply create a VM and tell it, yeah, use that disk, that VMDK. And you're up. Okay. Now from here, jump back to your main screen and carve your first VM. Bear in mind, you're all of 18, 20 minutes in from when you stood this thing up. Let's give our new VM a name. We'll call this one 24 Alpha. Give it a functional description if you like. Maybe this will be a net new SQL server. You can use tags if you want. In the Scale world, they're used for bulk operations, for sorting, for just generally making your life as a sysadmin easier. Okay? Don't have to if you don't want to. If it's going to be a Windows instance, tell us. We'll slipstream the paravirtualized stack in for you. Okay? If for some unknown reason, like you're going to do some of the crazy things that I do with my cluster, like run Windows 3.11 or OS2 Warp or whatever, you can also use legacy drivers like old 8139 NICs and so on and so forth. Okay. Tell us what type of boot environment your VMs need to have, be it BIOS, UEFI, doing some Windows 11 VDI stuff or some 2019 or newer Windows Server stuff where you need to have the VTPM for BitLocker, so on and so forth. Just tell us right here. Okay. Tell us how many cores you want. We'll give this guy, say, 4 cores and 16 gig of RAM. How many and what size virtual hard drives? Okay. Now, at this point, since we're doing one from scratch, pick which one of the ISOs that you uploaded you want to boot it from and hit create. You'll actually see the state machines in action here. Notice I'm loaded in through node 1, okay? But that VM has been created through the state machines instantiated through every node. Every node knows about it. Every node has direct access to those virtual hard drives. Now, when I start this guy, power that VM on, that sends a signal through the node that I'm currently logged in on, out via the state machines to every node in the cluster. They go and do a current and projected workload analysis and automatically determine where it makes the most sense for that VM to run. In this case, notice it shows node run here. Okay. Console, pop-up window. Even in the middle of an OS load, live migrations are trivial. Simply say, yep, move it. Where do I want to move it to? Let's move it over to node 3. Now, again, we don't need to deal with iSCSI ARB, ARB Win, SCSI Reserve, SCSI Release, any of that swinging data stores or object files around. Rather, we simply drop the thread on A, engage the thread on B, ship the running memory state over the backend node to node subnet, and we're done. That actually takes longer to describe than to do. He's already over here on node 3, but notice that there was more that happened there in the background than just a live migration. Okay. By taking the action of saying, hey, I want that over here on node 3, I also set affinity and anti-affinity. Okay. Without having to go hit a bunch of nerd knobs to do it. I just told HyperCore, hey, I want this guy to always try to start on node 3. So anytime in the future, it'll always try to start it here unless there's not adequate resource available, or if there is a node failure, it will move him around But as soon as node 3 becomes available, it will live migrate him back. Okay? Automated with something as simple as migrate from here to there. Even though it was in the middle of its OS load, it's a non-issue. Okay? Now, the other thing I want you guys to understand is the whole concept of different licensing levels is something we thought was freaking ridiculous. You know, with VMware prior to Broadcom, if you wanted high availability, fault tolerance, backup, site-to-site failover, failback, etc., you were buying Essentials Plus or Standard Enterprise more likely. Site Recovery Manager, licensing half a dozen different things, and then probably having to layer in a third-party solution as well. Well, with Scale, we just build all that in and don't charge any extra for it. We have low-level control of individual data blocks, doing things like taking snapshots, just inherent and takes milliseconds. We just insert a pointer into the scribe descriptor for the virtual hard drives. Any block behind that pointer, preserved in perpetuity. Any block after that, redirected to consume a different block instead. On top of that snapshot capability, okay, snapshots that the virtual machine itself has no access to, no visibility for, well, every single one of those snapshots are immediately clonable, startable, runnable. They're also mountable to any other virtual machine in the cluster. If you want to jump into last Thursday's snapshot and grab a simple file back that somebody changed by accident, it is literally no more complex than do this. You're there. You know, click and mount that one from that point in time to whichever machine, hit the mount it button. Okay. All of this, by the way, can be automated completely through the REST API as well. But in addition to all of the above, they're also directly clonable. And over the course of milliseconds, we will instantiate a brand new virtual machine from that point in time. Oh, sorry, clicked out of my browser window there. From that point in time, okay, and it takes milliseconds to do, even with some of my largest virtual machines. Here, we'll pick one that's got some size to him. This guy's got about half a terabyte, so we will jump in here, grab one of his snapshots. We'll grab one from last January. Okay, clone, clone, close. I'm not having to do any copy on writes, none of that silly overhead associated with. And he's already done, created, without affecting either the snapshot or the original VM. Now, notice that these are also replicating into the main product. We built in site-to-site replication. Any Scale workload will replicate to any other Scale target to which it has a route. In this case, I have in another data center across town, I have a node called Leviathan, big single node. Okay? Notice that as snapshots get taken, they also get replicated with differentiated retention schedules. I can keep them on Leviathan for 2 years if I want, depending on capacity, and only a week on my local side. That's actually handled through scheduling. I can show it to you if you want to see it, but it's there. Matter of fact, let's take that brand new VM we just created and set it for replicating. Okay, come into here. We'll pick a replication schedule and we'll replicate it to that same Leviathan node. Okay, instantly takes in a snapshot, grabs that snapshot, and if we jump back over to that Leviathan node, look what's already coming over here over the course of the next, hardly any time it's doing an OS install. Those objects will be here ready to start. Now, the reason that's useful, I can lose any drive anywhere, I can lose any node anywhere at any time, and everything just keeps going. But if the case of a, God help you, Joplin level event, where your site A gets wiped off the face of planet Earth, literally point a browser at site B, hit clone, and hit start. I can either clone from the most recent or dive directly into a point in time. Here's one that replicated earlier today, clone, close. And in the space of literally just a few milliseconds, with what, 4 clicks, here, we'll hard kill this guy. I have now failed that over to my DR site. Just built in, costs you nothing extra. It's all just part of what you get with scale. Want to fail back? That's fine. Replicate him back. We do block tracking on both sides. We won't bother to send blocks that we've already got on both sides. It'll replicate just the differentials back to site A. Once it's complete, hit clone, hit start. Again, well, just part of what you get. Okay? Now, we've covered a whole lot of ground while really only scratching the surface. You know, we haven't talked about multi-factor authentication. We haven't talked about, it's all there. We haven't talked about things like dedupe and compression, etc. It's all there. It's completely automated. It's just part of what you get. And the state machines handle it for you, so you don't even have to think about it. Here, dedupe saved me about 25 terabytes of space on this primary cluster. And I'm getting about 1.9 to 1 or so on my data efficiency. It's there. You just don't have to think about it. Kind of goes back to that whole notion of not needing to be a VCP and a CCNE and a SNIA certified storage engineer, but rather being able to focus your time on things that actually move your business forward rather than trying to figure out what cable got popped out or what power supply went up in smoke in the data center at 2 in the morning on a Saturday, right? We've also mostly talked about just single location here, because we've been focusing on how the individual sites. But let's say you've got more than one site. Say you've got 20 or 30 or 50 or 400 or 6,000 sites. Nobody wants to jump from browser window to browser window to browser window. Okay? Well, that's where that fleet manager piece I talked about early on comes into play. Okay? When you buy a scale cluster, one of the first things you receive are your fleet manager credentials. Before the gear even arrives, you can log into your fleet manager instance, come in here, hit add cluster, supply what you want the cluster name to be, what the IPs need to be, etc., and hit save. It'll wait there on fleet manager. When the nodes arrive, take them out of the box, stick them in the rack, stick them under the desk, whatever the location and use case is. Okay. Cable up the network cables, power them on and walk away. Don't even bother with hooking them up and configuring them. They'll come online, grab a locally assigned DHCP based IP, reach out to Fleet Manager and say, here I am, here's my unique ID. Fleet Manager goes, oh, you're going to be a cluster at this location. Find these other MAC addresses, find these other UUIDs. Here's what your IP config cluster name is, etc. Go form a cluster and get back to me. So the nodes do that. Zero touch. Okay. Cluster comes back in and says, okay, I'm up. Well, at that point in time, here through Fleet Manager, you can use our runbooks and Cloud Init and actually just push the workloads directly down to the clusters from right here. Again, without a human actually having to do anything. Really handy for, when your business is, say, a grocery store chain that's got, piles and piles of teenagers trying to be encouraged to continue to show up by a store manager who cares more about making sure that his inventory levels are under control and all of the things that go into that. What he's not is an IT guy, right? You can automate all of that directly here through Fleet Manager so that he doesn't need to have a business card that also says IT guy, okay? But where this gets far more interesting than just standing up the nodes themselves, those state machines that are harvesting all the data about everything going on the clusters in real time, and they're also self-healing it, self-load balancing it. They also report that data. And by the way, Fleet Manager here is totally optional, but they report that data up to your Fleet Manager instance so that at a glance from anywhere using any device through appropriate levels of authentication, etc., you can see everything going on in every cluster that you've got everywhere. For example, say this Trojan node. I can see it's got a warning. Okay. Store 5736, we'll say. But we'll click on him. I can see at a glance what his historic load levels, performance levels have looked like across the last day, week, month, year, so on and so forth, right? I can also see what his load levels look like, whether he's got a support tunnel open. By the way, we build in call home to every node for support. I'll get into that here in a few if you like. Which workloads are up, running, what their state is, etc. And without needing a VPN of any kind, I can go directly to that cluster from Fleet Manager, from my smartphone while sitting on a beach in Florida. No VPNs needed. That the state machines, it sets a flag on the fleet management side that says, hey, next time you check in, state machine, open a session back to me. And Fleet Manager reflects that session back to you, authenticated and secured throughout. I can get directly to not only the cluster as a whole, but I can actually drill directly into the individual workloads from anywhere with a simple single click. Boom. Making sense so far, guys?
Yep.
Okay.
Yeah, absolutely.
Now, you may have noticed something a bit different here. Over here on the far side, you saw version. We handle firmware updates very differently than what you're used to. The infrastructure you've got right now, or that you've had in the past, you had firmware updates to the subcomponent pieces from Dell or HP or Lenovo or Supermicro or whomever. You also had BIOS updates. Then you had updates for, say, the VMware stack or Microsoft updates for the Hyper-V stack, so on and so forth. Then you had storage updates, so on and so forth. In the scale world, that's a different animal. We always know exactly what the hardware is. So when we roll firmware updates out, it's every single level from the BIOS to the storage stack to the hypervisor itself, everything. We do roughly 600,000 regression tests against every single platform before we release. When an update is available, it lights up right here in the UI. Update available. I think I'm actually relatively current on all of my current clusters, so well, let's see if that Trojan one has got one available. We'll go directly to him here. Yeah, update available. Okay. When there's an update available, this lights up in the UI. Right here is a list of what has been changed, what's new, what bugs have been fixed, what new features are available, including a link to all of the iterative details about it. If you want that update, just hit apply update. It will download that update as a single object for every single layer to Node 1. State machines will then live migrate the workloads from Node 1 out to Node 2, Node 3, Node 4, so on and so forth. Okay. The node will sanity check itself, apply the updates at every single layer, sanity check itself again, reboot himself if necessary. Then the state machines will pull his workloads back to him and push the update over to Node 2. Wash, rinse, repeat. For 15 years now, every single update for a scale computing platform environment is been done hot on the fly with everything up and going at every single level with an actual single click. That one. Or right here in the UI, you can trip it off remotely. Now, like I said, we've covered an obscene amount of ground, and I think we're probably 15, 20 minutes long here. But there's a lot of information to convey. Before I go any further, I want to throw the floor open to questions, comments, thoughts, or concerns.
Running, I probably got to jump off myself, but the maybe just a little bit of a deeper dive on the how the backup or BCDR might differ from the snapshots in the Acronis, and also virtual switching, how you might set up different networks within the cluster and so forth.
Sure. So the easiest thing to do inside the scale cluster is we respect tag VLANs all the way down to the individual VM level. As you add NICs, you can tell it only participate in this tag VLAN and so forth. It's actually pretty trivial of a thing here. Let me do it on one so that you can see, right? And which tag VLAN you want it to be in. Easiest part of that. We can go deeper on that here in a minute, but let's go to your Acronis question first, because I actually run Acronis here in my environment. So let me fire that guy up. Oh, by the way, I wasn't kidding about Windows 3.1.1, but let me fire up my Acronis server here real quick. That's what those tags are for, by the way, is to make it so I don't have to sort through all kinds of things or start everything with a tag, stop everything with a tag, so on and so forth. Okay. I'll bring him online, but essentially the way that Acronis works, and it's not just Acronis, all of the various agentless backup players, and there's a few in the scale world, the way they all work is basically the same. They run a helper VM directly on the scale cluster. That helper VM talks to either my REST API stack or my Thrift API stack. I have full stacks for both. Okay. They take control of snapshotting. They snapshot the various virtual machines on whatever schedule you define in their application stacks, okay, in the backup package. They take those snapshots and mount them, much like I showed you, you could mount a snapshot, mount them up to their helper VM that's running on the node itself, okay? They then either use our change block tracking or their own change block tracking. In Acronis case, I believe they use their own change block tracking. They have some really good granularity stuff they do there. And stream the backup out to whatever the target may be, okay? On restore operations, they reach into the scale cluster. create a VM, unless you're, just restoring to the same VM. They'll reach into the scale cluster, create a VM, and populate it from the backup source, whatever that happens to be. Now, there's one other really cool trick they like to play. They actually have the ability in your legacy Hyper-V environment or your legacy VMware environment or any of those, you can drop their helper VM for those platforms in on them, or drop their agent in on physical servers. And let's see if that guy is up yet. We'll log into my Acronis management server. They will allow you to create a protection plan for those legacy platforms. And as part of that protection plan process, they have an option called Convert to VM, which allows you, regardless of what the source was, whether it was ESX or Hyper-V, yeah, it's still coming up, whether it's ESX or Hyper-V or physical servers or Rev or Zen or whatever, they will, as part of the backup process, reach into the scale cluster, create a VM to match whatever the source is, and post-process, as soon as the backup completes, populate that VM from the data that's still running over on the source machine, be it physical, virtual, whatever. They'll slipstream the paravirtualized driver stack in for you, etc., and happily act as a migration tool, as one of many migration tools, for those workloads as well. All right. Now, the way they work, incredibly simple and straightforward. I don't know how much of a tech deep dive you want to do on Acronis. I'll be more than happy to dive to whatever level with you. Much like Veeam does these days, Acronis is also use agentless, use agent-based, use both. There's no difference in cost or pricing structures. One of the coolest parts, though, is when you do publish agents out into your workloads, even if you don't use them for backups, those agents will discover what's normal for the workload they're published into. You've got an old 2K8R2 SQL instance running in production way past its sell-by date, but it's still there. You've never encrypted anything on it, and you push an agent into it. That agent discovers what's normal for that environment, and when it suddenly sees, a subdirectory structure or a virtual drive or whatever suddenly starting to get encrypted, it'll go, wait a minute, that's not normal. It'll identify the process that's doing it, notify you, and simultaneously isolate and kill the process that's doing it and roll the data structures back to their unencrypted state without you having to do anything. It's literally just part of what you get. I like to mention that because that functionality called active protection actually saved my bacon here in my environment. I had somebody actually trip off a WannaCry infestation on one of my servers. It caught it, stopped it, rolled it back, and killed the processes before I even knew something had gone wrong, before I bothered to pull out my phone and look at the notification. And it cost me nothing extra. It's just part of what you get. I know you were saying
that's awesome.
Oh, it's epic. If you get
Oh,
bored
yeah.
and
Yeah,
have
that's pretty good.
time, Google Acronis and WannaCry.
Yep.
Flip over to
Well, we
videos.
had
They
a
did a whole
WannaCry.
video of doing that. Yeah.
About 10 years ago. Yeah.
Oh yeah. Its derivatives still live to this day. But yeah, it's all just part of what you get. Costs you nothing extra. Oh, and I should also mention Acronis with us for scale is a perpetual license. Buy it once, own it forever.
Oh, nice. Yeah. Unbelievable.
That's something you never find in today's world, but that is very much the case. I know you were saying that you were tight on time here, so I don't want to drag it out longer than you need. But Yeah, they've got great low-level integration with us. So does Storeware, so does a couple of others. And off the record, I've been having discussions with Anton over at Veeam for the last 6 months as well. Unsurprising in a post-Broadcom world.
Yeah, this is excellent. I think, as you mentioned, there's so much more, but
Oh, there is. And
yeah,
trying to
Kyle,
squeeze it into
any
45 minutes and running over into an hour and a half. Yeah, and I've still only just scratched the surface.
Kyle, was there anything else on the GUI that you were? I mean, we definitely wanted to see more familiarity.
Sure.
Uh,
So the state machines, for example, right? Not only do they automatically figure out what's been going on and compensate for you, fix it for you, right? Not only will, I literally could walk over to the back of my cluster over here in the rack, rip out and power out a node 1 and or node 3, and you'd watch it flag is offline, all of his workloads come back up on the surviving nodes and just continue. If you got 5 minutes, I'm happy to do it. But it lets you know everything that it's seen and what it's done, along with the who did what to who for how many cookies stuff. You also can do things like create entirely local users with different levels of capability. Back in that spirit of who's allowed to do what to who for how many cookies, you can completely separate from your AD integrations and your credentialing pass-throughs and stuff. You can also do that on a purely local basis as well. The idea here is to not only make autonomous infrastructure, but autonomous infrastructure that needs no cloud connection of any kind to function perfectly. Okay. Let's see here. Schedules. We talked about snapshotting schedules, replication schedules, so on and so forth, right? Okay. We can, and here we'll pick one rather than create one from scratch. Pick one here and edit him so you can see what this looks like, right? Here I'm telling it, take a snapshot every day at midnight. Replicate it. On the local side, keep it for 4 days. On the remote side, keep it for 10. Okay. And I can change those frequencies all the way down to whatever level of granularity my bandwidth will allow. I want it to snapshot once a minute because I've got, dedicated 100 gig dark fiber between my locations. Go for it. Have a good time. Okay. Fairly complex constructs and concepts that we make incredibly simple. Okay. Remote clusters. Say I don't have a need for going to Fleet Manager, but I want to manage my local stuff. Local being relative. And like, for example, this Valkyrie node. We haven't talked about him at all. About 13 years ago, we partnered with Google, specifically because the way we do things from a technical perspective is incredibly similar, same hypervisor and everything, to the way that Google does things with the Google Compute Platform or the Google Cloud. We partnered with them to create what's called Cloud Unity. It's instances running on the GCP, running on Google Cloud, that are running the same image we put on bare metal. Okay, call it a node in the sky, but we took that to a whole nother level. Notice my IP scheme and notice the IP scheme of my local on-site stuff. We co-built with them a layer 2 VXLAN overlay so that replication target for you running in the cloud participates in your local LAN so that site A gets, slides off the end of the island into the White Sargasso Sea, point a browser at your Cloud Unity instance, will inflate it to add CPU, add RAM for you on an as-need basis. Hit clone, hit start, and you're now running from site B, only without having to change any of your networking infrastructure at all. Okay.
I think that was
Also,
one of
just
the
built in.
key elements I was thinking with the BRS, but that's fantastic right there because we have multiple sites, 16 sites worldwide, and we don't have good data center redundancy. And that's one of the things that we're trying to work towards with the new
Well,
solution.
that's part
Yep.
of why we created Cloud Unity with Google. Like I said, back in 2013, so about 11 years ago, I guess. You know, Scott VW and that whole crew over at Google worked intimately with them to get this all created, running, working. Runs beautifully. Actually runs at about 98% of bare metal performance levels. And there I
Is there
literally took a VM running on my primary cluster here, killed it and failed it over to Google Cloud with what, 2 clicks, clone and start.
Yep, and we would just need a GCP subscription or something along those lines.
We take care of all of it for you. Literally, we take care of all of it for you. We leave it from a CPU and RAM perspective deflated as much as possible, minimizes costs, right? And base it just on the storage size, number of replications, size of replications, footprint on disk that's actually being consumed. When you call us up and say, oh no, I've had a horrible, terrible, no good, very bad day, we jump in, inflate it to CPU and RAM that you're going to need, clone and start your VMs for you. We actually give you a run book and all of that, and biannual testing and all of that good stuff as well.
This is excellent. I probably gotta jump off. I have someone waiting.
Oh, understandable. We've run far longer than I intended to, but I want to make sure you guys have time to get answers to the questions you have.
Kyle, Tim.
No, this has been great. Thank you.
Yeah, happy to do it. Well, if you guys need to drop, go for it. That's perfectly fine. Let me do one thing for you before you do, and that's simply this. Right here on the screen, actually, let me do this here, is the email address I actually pay attention to, as opposed to the publicly facing one that gets constantly flooded with spam. Okay. You know, an hour from now, 2 days from now, whatever, you come up with oh shit, I should have asked about X, Y, or Z. Feel free to drop me a note. I'll be more than happy to take some time out of my day to answer it for you or connect you with resources or whatever you need. All right.
Excellent. Thank you very much.
Sure, no problem. Hey, Sam, I know that we went way more technical than you might have been asking for or looking for, but were there questions still outstanding in your mind about things you wanted to understand?
No, it was technical, but I was happy to listen in. And like I said, we've just started our venture, learning about scale. But this was certainly helpful for me. Thanks very much.
More than happy to. And, you know, same offer stands for you. If you want to, you know, dive more deeply into competitive discussions, you know, how we stack up against Nutanix or SimpliVity or Pivot3 or Maxstar or
Yeah.
VMware or any of those, I'll be more than happy to set up some separate time for you, and we can dive directly into all of that as well. just drop
I
me a
really
note at that
appreciate
same
it.
email address.
Okay, I will do.
This one right there.
Okay, fantastic. Thanks, Alan.
Happy to do it, and a pleasure to meet all of you. Look forward to hearing from you, and if you need anything, don't hesitate to reach out, okay?
Thank you.
Thank you
right,
very
thank
much.
you.
Thanks, guys. Take care.
Cheers.
All right.
Bye-bye.
Have a great day.
You too.
Bye-bye.
Bye-bye.
Cheers, guys. No, but where's the email address?